Let's take a look at another example of Newton's second law in 2 dimensions involving forces at angles. Timmy drags his trunk of toys with a mass of 25 kilograms across the bedroom floor. He applies a force of 30 newtons at an angle of 40 degrees, and the trunk accelerates to the right at 0.5 meters per second squared. Draw a free body diagram for the trunk. Make sure the magnitudes of the forces are accurately drawn and that the forces are clearly labeled. This word pops up in physics quite frequently, and sometimes students just forget what that even means. The word magnitude just means the value. That's without the direction. Okay, magnitude and direction together make up a vector, but just the magnitude is a fancy way of saying the value of the force. All right, here we go. So first of all, Timmy is going to be pulling this trunk. We have this 30-degree pull. I'm going to call that an applied force. Of 30 newtons, and we know this angle here is 40 degrees. There's a force of gravity on the trunk, which is equal to the mass times 9.8 meters per second squared, and that is 245 newtons. Okay, the trunk is being supported by the floor, so there's a normal force on it. We don't know what that is, and there is also a force of friction on the trunk, which we will see more clearly later. And since he's dragging it across the floor and the trunk is sliding, that is a force of kinetic friction. And we don't know what that one is. Okay, so 4 forces acting on the trunk. Here we go. Determine the magnitude and direction of the net force exerted on the trunk. Okay. Well, first of all, we're told that the acceleration is to the right in this part, right? It says accelerates to the right. So if it accelerates to the right, then the net force is also going to be to the right. So when I'm looking at the net force, I can really just consider the horizontal direction only, right? So the net force in the x direction is the mass times the horizontal acceleration. The mass is 25 kilograms, and that horizontal acceleration is half a meter per second squared, right? Grabbing that from right here. So this is 12.5 newtons, and it, of course, is going to be to the right. Okay, that's the net force. All right, continuing, calculate the normal force exerted on the trunk by the floor. So the normal force is a vertical force, so what's going to be most helpful to me is to look at the sum of the forces in the y direction, and since the acceleration is to the right, I know that the sum of the forces in the y direction is going to be equal to 0. In other words, the trunk is not accelerating up or down. It's only accelerating horizontally. So if that's the case, then I can write an expression for the sum of the forces in the y equal to 0 like this. So there's going to be a few forces that have vertical components. The normal force has a vertical component. The applied force has a vertical component. Force of gravity has a vertical component. So I'm just going to pay attention to those 3. Okay? So summing the forces in the y means I've got the normal force upwards plus the vertical component of the applied force. So I'm going to take that times the sine of 40 degrees. And then I'm going to subtract the force of gravity. Okay, setting those equal to 0. All right, the normal force I don't know. The applied force is 30 newtons. And the force of gravity is 245 newtons. So setting those equal to 0, adding 245 to both sides, well, actually moving this whole term over to the right side will give me what the normal force is. So I get 225.7 newtons is the normal force. And I can go ahead and add that up at the top to my free body diagram. So I now know that this is 225.7 newtons. Okay, let's keep going. Next question, calculate the coefficient of kinetic friction between the trunk and the floor. Well, before I can calculate the coefficient of kinetic friction, by the way, that's usually written this way, the Greek letter mu with a little k after it, coefficient of kinetic friction. Before I do that, it's going to be more useful for me to find out what the force of kinetic friction is. And once I have that, I can get the coefficients. Okay, so to get the force of kinetic friction, I'm going to now sum the forces in the x direction and set it equal to the net force. So here we go. If I sum the forces in the x direction, it will equal, well actually I have that, right? It's going to equal 12.5. And then let's just come up with an expression for the sum of the forces in the x direction. So which forces have horizontal components? Well, this is going to have a horizontal component, and this is going to have a horizontal component. So adding those up, here we go. So that applied force, Timmy's applied force, times the cosine of the angle, 40 degrees, and then plus the kinetic friction force, which is to the left, so I'm making that negative. Those are going to be equal to 12.5 newtons. Okay, so this is 30 newtons times the cosine of 40 degrees minus F kinetic equals 12.5 newtons. And that means this force of kinetic friction is 10.48 newtons. Now, part two, I'm going to continue. Now that I know what the force of kinetic friction is, and I'm just going to go ahead and label that on my diagram up here. So this is 10.48 newtons. Now that I have that force, I can get the coefficient this way. By definition, the force of friction on any object is equal to the coefficient times the normal force. Okay? Well, the force of friction is 10.48 newtons. The coefficient is what I'm looking for. And the normal force I have from up here, right? I already found that one. So I'm going to multiply by 225.7 newtons and get that this coefficient of kinetic friction is 0.046. And the units technically are newtons per newton. And you can write it like that, or you can say that newtons per newton cancel out and become nothing. And so usually people don't include the units of newtons per newton. Okay, now some conceptual questions. So let's go back and take a look at this force that Timmy is putting on the trunk. So here's the trunk, right, along the ground, and Timmy's got that force here. And it's originally at an angle of 40 degrees. Here we go. If Timmy decreased the angle of his applied force, but kept the magnitude constant, so he kept pulling with that same 30 newtons, how would each of the following forces on the trunk change? Okay, so we're talking about going from this kind of angle to maybe an angle like this, like maybe like down here. That almost looks like no angle. Just decreasing the angle a little bit, okay? So theta is going to be less than it originally was. So if he decreases the angle, what's going to happen to the normal force, the frictional force, and the weights, okay? Well, if we consider the other forces, so here's the normal force, here's the weight, which which is the force of gravity. And here's that friction force, which I called F kinetic before. It's the same idea. Well, if you look at the sum of the forces in the vertical direction, these three forces are all acting vertically. Specifically, the normal force and Timmy's applied force are both counteracting gravity. So if the force decreases and moves to the purple force, if the angle of that applied force decreases, then the vertical component of that force goes down. Okay? And if the vertical component of that applied force goes down, then that means that the normal force has to do more of the work, so to speak. The normal force is going to take more of the force of gravity than the other one. Okay? So the normal force is going to have to increase as a result of that. Again, because the applied force in the vertical direction is going to be less. Therefore, the normal force will have to be more to compensate for the loss of the vertical component of the applied force. Okay? What about the frictional force? Well, we looked up here that the frictional force was equal to the coefficient times the normal force. Well, if the normal force increases, if this goes up, then the frictional force will necessarily increase as well because it's dependent on the normal force. So the frictional force will increase as well. And if you think about this in real life, right, Timmy isn't pulling upwards on that crate as much as he was. And so, of course, it's going to experience more friction because the box is actually rubbing against the ground with more force than it was before. Finally, what about the weight of that, of the trunk? Would that change? Well, remember the weight is the force of gravity, which is just equal to the mass times the acceleration due to gravity. The mass is always 3 kilograms no matter what. The acceleration is going to be 9.8 meters per second squared no matter what, as long as the trunk doesn't change to some different planet. So the weight will stay the same. No change to that weight.